So, you might have seen some of those pretty wild headlines recently. I know I did.
Oh, yeah. What caught your eye?
Stories about an Asian country apparently using a laser to attack another country's military plane.
Right, I saw that. It sounds like something straight out of Star Wars, doesn't it?
Exactly. But it wasn't some science fiction movie. They're
Yeah.
saying it was real. And honestly, it's a bit scary, but also, I don't know, there's something about it that's just deeply fascinating.
I get that. The technology itself is pretty incredible when you think about it.
It really makes you wonder, though, right? How does light, light, it's so ordinary, fills this room right now. How does that become powerful enough to actually damage an aircraft?
That's the million-dollar question.
And, if you're anything like me, you probably remember sitting in, like, high school physics or chemistry class.
Oh boy, here we go.
Haha, yeah. And thinking, why on earth do I need to know about J.J. Thomson discovering the electron? Or Niels Bohr and these energy levels? What does an excited state even mean outside of a textbook?
You're nodding along, I see.
Totally. Well, look, our goal today in this deep dive for our Today's Aha Moment channel is really to connect those exact dots for you, for everyone listening. We want to take you from maybe feeling a bit lost about the science to actually getting it, to understanding the world around you a bit better.
And you've really hit on something crucial there. For such a long time, science education often felt like just memorizing definitions.
Right. Like flashcards.
Exactly. You'd learn photoelectric effect is the emission of electrons when light, blah, 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 or excited state is when electrons occupy higher energy levels. You could maybe recite it for a test.
But did you really know what it meant? Or how it applied?
Precisely. You rarely saw the connection between those definitions and, well, amazing technologies like the laser that literally shape our modern world. It's a perfect example of how those seemingly abstract chapters suddenly become very real.
And lasers are everywhere now, aren't they? It's not just military applications. We see them. Well, laser pointers, obviously. Barcode scanners in the supermarket checkout line.
CD players, if anyone still has those.
True. But also, like, dental drills. High-speed machines cutting through thick metal. Even delicate stuff like eye surgery or tattoo removal.
Hair replacement, complex measuring systems. The list goes on.
It's woven into everything. But that just brings us back to the question, if light is just light, what makes laser light so different? So powerful.
Okay, yeah. Let's unpack that. Where do we start?
Well, let's start at the beginning. The real basics.
All right. So to really get lasers, you have to start super small. Think about an atom. You've got the nucleus in the middle, right?
Protons and neutrons.
Right. And buzzing around it, you have electrons. Now, these electrons, they don't just float anywhere. They exist in really specific energy levels or orbits. You can kind of picture it like rungs on a ladder.
Okay, discrete levels.
Exactly. And an electron naturally wants to be on the lowest possible rung. That's its most stable spot, its ground state energy level. Any rung higher up is what we call an excited level.
So it takes energy to climb the ladder.
Precisely. And that's the key interaction. Electrons can absorb energy maybe from heat or light hitting it or an electrical current. And when they absorb just the right amount, they jump up to a higher, more excited energy level.
Sure.
But here's the thing. They don't like being up there. It's unstable. They want to return to that comfy ground state.
Makes sense.
And when they drop back down, they have to release that extra energy they absorbed. They do that by spitting out a tiny packet of light, a particle we call a photon.
So the jump down creates light.
That's the essence of it. You see this constantly. You turn on a toaster, the element glows red. That's atoms in the metal getting heated up, electrons jumping up and falling down, releasing red photons.
Or like an old CRT television screen.
Perfect example. Electrons hit the phosphor coating, excite the atoms, they fall back down, and boom, light, creating the picture.
Wow. So these tiny electrons jumping around are the source of light we see. And this connects back to those scientists, right? The ones that felt so, I don't know, historical and abstract in class.
Absolutely.
Like J.J. Thomson, way back in 1897, discovering the electron in his lab. He had no idea, presumably, that he'd just found the key ingredient for something that could one day, damage an aircraft with light.
Not a clue. And then Niels Bohr comes along a bit later and figures out the straw why electrons stick to these specific energy levels. It wasn't just random floating.
So they weren't just facts to memorize. They were finding the actual rules for how light gets made.
They were laying the foundation step by step. Now think about that neon sign again. Lots of excited atoms, lots of photons being released as electrons drop down. But they do it randomly.
How so?
Well, one atom might release its photon now, another one a millisecond later. One photon goes this way, another goes that way. Their light waves aren't lined up at all. We call this spontaneous emission. It's just happening whenever the atom feels like it.
Okay, so it's chaotic light.
Exactly. It can be bright, like a neon sign or a regular light bulb, but the light is scattered, it's diffuse, it's incoherent. And that kind of light, no matter how bright you make it, just isn't focused enough to do something like damage an aircraft. It spreads out too quickly.
Right, so that was the big problem now. How do you take this random, messy light and turn it into something directed, something powerful?
That was the challenge. And for a long time, spontaneous emission was pretty much the only way we knew how to get light out of atoms reliably.
Okay, so here's where it gets really interesting, isn't it? This is where the story kind of shifts gear.
This is where the genius comes in, because it raises that critical question: how did we bridge that gap from the gentle glow of a neon sign to the focused power of a laser?
Yeah, what changed?
The answer, or at least the crucial theoretical seed, came from Albert Einstein, way back in 1917.
Einstein again, of course.
Yep. He wasn't thinking about lasers specifically, but he was thinking deeply about how light and matter interact. And he predicted something called stimulated emission.
Stimulated emission. Okay, what's that?
So imagine you have an atom and its electron is already in an excited state. It's ready to drop down and release a photon, but it hasn't done it yet.
Right, hanging out on a higher rung.
Exactly. Now, Einstein theorized that if another photon comes along and this incoming photon has precisely the right amount of energy matching the energy difference between the excited state and the lower state,
Okay.
it can actually stimulate or trigger that excited electron to drop down right then and there.
It gives it a nudge.
Kinda. But here's the really mind-blowing part. When the electron drops down because it was stimulated, the photon it releases isn't just any photon, it's an exact clone of the incoming photon.
A clone, what do you mean?
I mean identical in every single way. Same energy, which means the same color, the same wavelength, same phase, meaning their light waves are perfectly lined up, marching in step, and crucially, traveling in the exact same direction.
Wait, so one photon goes in and two identical photons come out traveling together.
Precisely. It's like light amplification at the most fundamental level. One photon triggers the release of a perfect copy of itself.
This is completely different from spontaneous emission, where they just pop out randomly.
Totally different. This was the huge conceptual leap. Einstein basically showed that under the right circumstances, you could get light to trigger the release of more light, perfectly coordinated light, in this amazing domino effect.
The domino effect of photons.
Yeah.
Wow, that suddenly sounds like it could build up into something powerful.
Exactly. It laid the theoretical groundwork for creating a beam of perfectly aligned, identical photons. It fundamentally changed how we thought about controlling light.
And people actually ran with this idea, right? It didn't just stay as theory.
Oh, absolutely.
Yeah.
It took time, but brilliant minds built on it. You had Charles Towns and Arthur Shallow in the late 1950s figuring out the theory for the maser, which does the same thing, but with microwaves instead of visible light.
Maser. Microwave amplification by stimulated emission of radiation.
You got it. And then the big moment, 1960, Theodore Maiman, working at Hughes Research Labs, built the very first working laser light amplification by stimulated emission of radiation using a synthetic ruby crystal.
Wow, 1960. So these weren't ancient historical figures anymore. These were real people solving real engineering problems based on that physics insight from Einstein decades earlier.
Real people, step-by-step innovation. Taking that fundamental idea of stimulated emission and figuring out how to make it happen reliably, how to build a device around it.
Okay, so this brings us back to that aircraft-damaging laser we talked about at the start.
Yeah.
What's the actual secret sauce? How does all this physics translate into that kind of power?
Right. So what is the core principle that takes us from blinking atoms to a beam that can burn through metal? This really leads us to our aha moment for today, I think.
Let's hear it. What's the big takeaway?
When you hear about a laser powerful enough to damage an aircraft, it's easy to imagine some kind of, mysterious new energy weapon.
Yeah, like alien technology or something.
Right. But the aha moment is this. Lasers aren't about a fundamentally new type of light. They're about an incredibly clever, incredibly precise way of controlling and amplifying ordinary light. It's all about orchestrating those basic physics principles, how electrons gain and lose energy, how photons behave, and using ingenious structures to make those photons work together in a way they never would naturally.
So it's not magic light. It's engineered light, controlled light.
Perfectly put. It's taking those fundamental rules we learn about in physics and chemistry and applying them with incredible ingenuity to create something extraordinarily powerful. That's the aha.
Okay, I think I'm starting to see it. It's about control.
Exactly. So let's unpack that aha a bit more. What are the key ingredients for that control?
Please do.
First, obviously, is that stimulated emission we just talked about. That's the heart of it. Remember, an incoming photon triggers an excited electron to release an identical photon, same energy, same phase, same direction.
The cloning process.
Right. And this cloning process is what gives laser light its defining characteristics. Because all the photons are identical in energy, the light is incredibly pure in color. We call it monochromatic. Unlike a flashlight beam, which is a jumble of different colors, laser light is typically one specific wavelength.
Okay, one pure color.
Second, because they're all emitted in sync, their waves are perfectly aligned. We call this coherent. Think of it like soldiers marching perfectly in step versus a crowd just milling about. Coherent waves add up their energy much more effectively.
So they reinforce each other.
Exactly. And third, because they all travel in the same direction, the beam is highly directional. It doesn't spread out much over distance unlike a flashlight beam that diffuses quickly. This allows you to concentrate the energy onto a very small spot.
Monochromatic, coherent, directional. That's what makes it different from my desk lamp.
Fundamentally different. Now, the second ingredient is achieving something called population inversion.
Population inversion. Sounds upside down.
It kind of is. See, normally in any group of atoms, most electrons are lazy. They prefer to be in the low energy ground state. Only a few are typically in an excited state at any given moment.
Okay, that makes sense. The natural state.
Right. But for stimulated emission to be the dominant process, rather than atoms just absorbing the light, you need the opposite situation. You need more electrons hanging out in the excited state than in the ground state. That's population inversion. The population is inverted from its normal state.
How do you manage that? It sounds unnatural.
It is. You have to actively pump energy into the system, the laser medium, which could be a gas, a crystal, a liquid. You might use intense flashes of light, like Maimon did with his ruby laser, or a strong electrical discharge, like in gas lasers. You're basically forcing a majority of the electrons up into that excited state, ready to be stimulated.
So you pump them up to create this inverted population.
Precisely. And engineers figured out clever ways to do this efficiently. Some early lasers, called three-level lasers like Ruby, needed a lot of pumping power because the ground state was involved directly. Later, four-level lasers were developed, which are much more efficient because the electrons drop to an intermediate level first, making it easier to keep that population inversion going.
Okay, efficiency matters.
Big time. And the third key ingredient is the optical cavity or optical resonator. This is usually just a pair of mirrors.
Mirrors, how do they help?
They are absolutely crucial. Imagine your laser medium, say, the ruby rod or the tube of gas, with a mirror at each end facing each other.
Okay, got it.
Now, when stimulated emission starts happening, photons are created. If a photon happens to be traveling along the axis between the mirrors, it will bounce off one mirror, travel back through the medium, hit the other mirror, bounce back again.
Back and forth, back and forth.
Exactly. And each time it passes back through the medium, what does it do?
It stimulates more emissions. It clones itself.
Right. So you get this cascade effect. The light bounces back and forth, maybe hundreds or thousands of times, building up intensity, stimulating more and more identical photons that are all traveling perfectly parallel to each other between the mirrors.
Wow, trapping the light to amplify it.
That's the idea. And then one of the mirrors is made slightly transparent. Maybe it reflects 99% of the light, but lets 1% pass through. That 1% that escapes is your laser beam, incredibly intense, perfectly aligned, coherent, monochromatic light.
That's brilliant. So simple, yet so effective. Stimulated emission creates the clones. Population inversion makes sure there are atoms ready to be cloned, and the mirrors build up the intensity and select the direction.
You've nailed the three core pillars of how a laser works.
Okay, can we look at a specific example, maybe one people have seen?
Sure. A really common one, especially in labs or, like you said, barcode scanners, is the helium-neon laser, the He-Ne laser. It usually makes that familiar red beam.
Right, I know that one.
So inside a glass tube, you have a mixture of helium gas and neon gas. And you have the mirrors at the ends, of course. Helium and neon.
Okay. You pass an electrical current through the gas mixture. This electrical discharge pumps energy primarily into the helium atoms, exciting their electrons.
Okay, so helium gets excited first.
Yes, but Helium itself isn't great at lasing in this setup. However, an excited helium atom happens to have just about the right amount of energy to efficiently transfer that energy to a neon atom when they collide.
Ah, like passing a baton in a relay race.
Exactly. It's a very efficient energy transfer.
Yeah.
So the helium gets excited by the electricity, bumps into a neon atom, and excites the neon atom. Now, you have lots of excited neon atoms. You've achieved population inversion in the neon.
Got it. Neon's ready to lace.
Right. Then an excited neon atom spontaneously emits a photon, or a stray photon starts the process. That photon stimulates another excited neon atom, which releases an identical photon. Those bounce between the mirrors, stimulating more and more neon atoms.
And out comes the red laser beam from the slightly transparent mirror. Precisely. A narrow, coherent, intense red beam, all thanks to excited helium passing energy to neon, stimulated emission in the neon, and the amplification from the optical cavity. It's a beautiful little dance of atomic physics.
That makes so much sense seeing it laid out like that. But okay, that little red Heaney beam is pretty harmless, right? You shouldn't stare into it, but it's not going to damage an aircraft.
Absolutely not. A typical Heaney laser might only have a power output measured in thousandths of a watt.
So how do we get from milliwatts to something? Military grade.
Scale, power, and engineering. The fundamental principles, stimulated emission, population inversion, optical cavity, remain exactly the same, but military lasers operate on a vastly different scale. We're talking tens of kilowatts, hundreds of kilowatts, even megawatts of power.
Megawatts. That's millions of watts.
Yeah.
Compared to thousands.
Huge difference. And it's not just the raw power, it's that incredible focus and coherence we talked about. Because the laser beam is so directional and coherent, it can be focused down to a tiny, tiny spot, even over very long distances.
It doesn't spread out like a flashlight.
Barely at all. So you're concentrating potentially megawatts of power onto an area maybe the size of a coin. That creates an enormous power density at the target.
And that's what does the damage.
That's what does the damage. It can overwhelm sensors and cameras on an aircraft, burn through surfaces or paint, disable sensitive optics, or tragically even blind pilots if directed improperly.
Wow. And I guess they can deliver that power differently too.
Yes, that's another factor. Some lasers are continuous wave, CW, delivering a steady beam. Others are pulsed lasers, delivering their energy in incredibly short, extremely intense bursts. These pulses can sometimes have even more destructive effect on materials.
So it's the same physics as the barcode scanner, just scaled up massively and focused intensely.
In essence, yes. More powerful laser mediums, much more aggressive pumping mechanisms, very sophisticated optics for focusing and beam control, but the core physics is identical.
This is really incredible. When you think back to those chapters in the textbook that maybe felt a bit dry, atomic structure, energy levels, electrons jumping, photons, that photoelectric effect thing, spontaneous versus stimulated emission, population inversion, optical cavities, even knowing about specific elements like helium and neon and how they give off light.
All those pieces.
They're not just random facts anymore. They are literally the blueprint. They are the exact ingredients you need to understand and maybe even design something as advanced and, frankly, powerful as a laser. It makes the science come alive, doesn't it?
It really does. And that's the beauty of it, I think. This isn't just about memorizing definitions or historical names. It's about seeing that physics and chemistry aren't somehow separate from the real world. They are the explanation for the real world.
The instruction manual.
Exactly. And understanding them deeply, truly getting how these principles work, doesn't just let us understand fancy gadgets. It allows us to create, to innovate, to solve problems, to contribute meaningfully. It connects the tiniest quantum interactions inside an atom to technologies that have global impact.
It's empowering, actually, to know that understanding these fundamentals unlocks so much.
It truly is.
Because who knows, right? Maybe that next ordinary chapter you study in physics, the one that seems a little boring or abstract right now, maybe that holds the key.
The key to what?
The key to the next breakthrough. Maybe it's the secret to building an even better laser or figuring out how to power a spacecraft to Mars or transforming the world in some way we haven't even conceived of yet. The potential is hidden in those fundamental principles.
Well said. The potential is definitely there.
Well, we really hope this deep dive gave all of you listening a powerful aha moment today. It certainly did for me, connecting those classroom concepts to something so tangible and, well, impactful.
It's always fascinating to revisit the fundamentals.
If you enjoyed this exploration into how light gets its power and how lasers work, please do hit that like button, subscribe to our channel, Today's Aha Moment, and maybe share this with a friend who's also curious about how the world really ticks.
We appreciate you tuning in.
Thanks so much for listening, everyone. We'll catch you on the next deep dive.